All right, welcome back to Mr. P Helps with Calculus. We have Unit 5, Day 1, EVT, otherwise known as the Extreme Value Theorem. We're talking about extremes that could be either maximums or minimums. As we jump right into it on our first definition, so extrema is a word you're going to hear me say quite a bit of a function, are either maximum or minimums, as I just mentioned, and they can either occur at two different places. They can occur in the middle of a function, which would be either at some sort of crest at the top of like a wave or a bottom of a wave, or they could be on the endpoint. So they could be on the interior points or the endpoints. And here I'm going to show you some diagrams of how they could look like, I should say, for both of those examples. So we have a maximum and a minimum could be on the interior. So this is like I was talking about. So anytime you have like a sinusoidal graph like this one, so you're going to have that top of the wave, which would be your maximum, and the bottom of the wave would be your minimum. And that is on the inside, the interior of that function. Or it could happen on the endpoints. On this function, we can see that the maximum part of the function would be right here on this endpoint, and the minimum would be at the right-hand side, which would be also an endpoint. Now, maximum minimums don't have to be on both ends or both interior points. They could be on one endpoint and one interior point. Like in this example, we have the minimum is an endpoint and the maximum is an interior point, or the other way around. All right, so EVT. So this extreme value theorem, all it states basically is if you have a continuous function that is closed over an interval from a to b, could be from any numbers, then that function has to have a maximum and a minimum. Now, if you look at this graph right here, it has to have a maximum and minimum. Why? Because this is a continuous function. There's no breaks, no jumps. It is continuous over the entire function, and it is on a closed interval, so meaning it doesn't have holes on the endpoints. Now this one is exactly what I just said a second ago. This one, EVT cannot be applied to this graph, and the reason why is because its endpoints are holes. So it's not on a closed interval. So it's an open interval. Open interval, obviously, because it's an open circle. And then this last example has a removed discontinuity in the middle. So therefore, EVT cannot be applied. And on the AP exam, you do have to state, you can just say EVT. You can actually use the abbreviation, but you do have to state that the function is continuous over that closed interval and give that interval. All right, so the way we're going to use this, because when they give you a question, they're not necessarily going to give you a graph. They're just going to give you the function itself, and you're going to have to determine if EVT can be applied. And what we're going to look for is the first derivative, because the first derivative, if it happens to be 0, then we know that that has to be either a maximum or a minimum, or a relative minimum. When I say relative, it doesn't have to be the absolute maximum. It just has to be the maximum of that wave, that sinusoidal wave. Or it doesn't have to be sinusoidal. It could be, in this case, it would be a parabola. So that point right there is at the lowest point of the parabola, so therefore it's a minimum. And what you notice about that point is the slope of the tangent line happens to be 0. The same thing will happen for a maximum. That point right there is also going to have a slope of 0 for that tangent line. Anytime that occurs, that means anytime the derivative, f prime of c, equals 0, you know that's either going to be a maximum or a minimum. Now, which one it is, you'll have to determine a special way, which we'll get to the first derivative test later on. This EVT cannot be applied here. This is a corner and cusp, and remember also vertical tangent lines mean it's not differentiable. So it does not exist at that point, because as we've mentioned in prior videos, the slope must change continuously at minute amounts. If x equals c is a critical value point, then f of c is a critical point. So that just means that this point right here happens to be that critical value point. Now, absolute extrema can only occur at a critical point or an endpoint, and that is important. You must test not just the critical value points, you must test the endpoints as well, which we'll talk about, like I said, when we get to this first derivative test. Relative extrema occur only at critical value points. So this is your relative maximum, relative minimum. This would also be a relative maximum. It's not as tall as this one, but this is also a relative maximum. Now, this point happens to be what's called the absolute maximum because it is the highest of all the maximums. Same thing goes for this endpoint, would also be the absolute minimum. So if f has a relative minimum or maximum of x equals c, then c happens to be a critical value point. We happen to have 4 critical value points. There are 4 places where the tangent line happens to be a slope of 0. To find these extrema on a closed interval, first find the critical value point of f on that closed interval from a to b. Evaluate f at each critical value point, and you're going to see me do this on the next slide. I'm actually going to follow these instructions. Number 3 says evaluate f at each endpoint, so you have to find the endpoints because, as I've already shown you in the diagrams, the endpoints could be the absolute minimum and maximums. In fact, in this case, the endpoints are both. So you have to always test the endpoints. And then number 4 says least of these y values is the minimum, and then the greatest one is obviously the maximum. And that's all you're really doing is you're plugging those critical value points into the original equation to see which is the largest and which is the smallest, because you're not going to be given the graph. Here's a perfect example of exactly what I'm talking about. It says find the extrema of f of x if the function is 3x to the 4th minus 4x to the 3rd on the interval from -1 to 2. Now, -1 is the start of our interval. This is a closed interval, and 2 is the end of that interval. You always need to check the endpoints, but you also need to check the critical value points. And that would be the places when the derivative happens to equal 0. So we're going to first use our simple power rule to find the derivative of this function, and that's where I got this line from. Then we're going to set that derivative equal to 0, and we're going to solve it using whichever way you can solve it. In this case, I'm going to factor out the GCF. Both of these terms can both be divided by 12x squared. And once you factor that out, then you can use your zero product property, as you've probably done 100 times by now, and solve for the 2 critical value points. And these happen to be the 2 places, the 2 x values, that have a tangent line where the slope is 0, because that's what our derivative is. It's our tangent line at all the given x values, and once we set it equals 0, we know the slope is 0 at these 2 x values. But that is not our answer. We don't know what the max and minimum are yet. Remember, that's where we use EVT. We're going to apply EVT to find what is the extremes, the absolute max and the absolute min. We have to first test -1 and 2. I did -1 first. I did 2 actually last. It doesn't matter what order you test them in. And all I'm doing is I'm plugging them into the original equation. Very important, don't make the mistake and put it into the derivative, because we don't want to know what the slope is. We actually already know what the slope is, 0, except for the endpoints. We want to know what the height is. We want to know what f of 0 is by plugging it into the original function and then just using your algebra skills to find the height at that point. And then the last thing we do is just look at our 4 heights and determine which one's the biggest and which one's the smallest, and that's it. Absolute maximum is the biggest at x equals 2, which happens to be 16. And the absolute minimum happened to be at -1 when the height was, the height was -1 at 1 is what we got right here. All right, example number 2. Find the extreme of f of x of 3x to the 4th minus 12x cubed on the interval from -1 to 2. Very similar question. I'm going to solve it the same way. I know I have to test the 2 endpoints. So that's a given. I can always write that over here to the side, f of -1 and f of 2. And it looks like we're also going to have 1 critical value point. And the way I do that is use my simple power rule to find the derivative, set that derivative equal to 0, and solve it. In this case, once again, I can pull out the GCF, 12x squared, and then solve for it, and I end up getting 0 and 3. Now you might be wondering, why didn't I test 3 over here? Now you could test 3, but it would be a waste of your time because 3 is not over the closed interval that they gave you. So don't waste time finding something that, actually if you put that, it might end up being bigger than the other numbers. It might actually make you get the wrong answer. So always be careful and check what closed interval are they giving you, and make sure you do not test for the height of one of those points that's not on the interval. And I think that's going to be it. Thanks again for watching, and I will see you on the next video.